Assalamu alaikum. Welcome to our presentation on the CSE-106 mini project. Our project focuses on two distinct yet fundamental areas of computer science: time complexity analysis and graph-based social network simulation. The next slide introduces our team and instructor. This work was conducted under the guidance of our respected instructor, Dr. Nafis Sadek. I'm Sumay Sodagu Shoshita, and my other two teammates are Mohammad Faizullah Talukdar and Mohammad Shahriar Hussain Siam. Let's look at the overall project overview. Our project is divided into two parts. Part A is an empirical study where we measure the actual execution time of linear search for different input sizes and compare it with the theory. The experiment confirms that the execution time increases proportionally with the input size n, which perfectly matches the theoretical big O of n complexity. Part B simulates a social network using an undirected graph to analyze key graph properties like degrees, edges, and connected components as the network size grows. The slide highlights the core problems addressed in the project. The two specific problems we addressed are Part A, time complexity analysis, specifically the empirical time complexity analysis of linear search, and Part B, graph-based social network simulation, where we focused on creating a friendship graph using an undirected graph. We now dive into Part A, time complexity analysis. Let's begin with Part A, time complexity analysis, focusing on the empirical time complexity analysis of linear search. Moving on, the slide outlines the specific objectives for Part A. The specific objectives for Part A were threefold. First, to implement linear search using C programming and measure the average execution time. Second, to analyze the effect of input size by plotting the execution time against the data size. And finally, to verify the empirical complexity with the theoretical complexity. This slide provides a brief introduction to our study on linear search. This project presents a practical empirical study of the linear search algorithm. By testing the algorithm across various input sizes, we measured the average execution time. The goal of plotting the resulting graph was to verify that our experimental results align with the known theoretical time complexity. We can confidently say the result confirms that linear search adheres to big O of n time complexity. This slide covers the theoretical foundation of linear search. As a quick review, linear search is a straightforward algorithm that works by sequentially checking each element of an array with the target value until a match is found. In terms of time complexity, the best case is big O of 1. Both the average case and the worst case complexity are determined to be big O of n. This slide details the software and tools we utilized. To perform this analysis, we used the C programming language for the search implementation. We specifically relied on the time H library to accurately measure the execution time, and Python was then used for plotting the resulting data, which was stored in a CSV file. The next slide explains our experimental methodology. Our methodology involved several careful steps. We first generated a random array of size n and selected a random target. We applied linear search and measured the execution time. Critically, we repeated this process 1000 times to ensure we found a stable and reliable average time. We then repeated this entire process for all tested value of n to generate data for our final plot. We now review the table summarizing our empirical results. Here is the table showing our measured results. You can see the relationship immediately. For an array size of 10,000, the average search time was 0.157 milliseconds. When the array size increased 5 times to 50,000, the search time also increased roughly 5 times to 0.657 milliseconds. This slide presents the graph for our data analysis. This visual representation of this data is presented in this graph. The x-axis represents the array size and the y-axis represents the average search time in milliseconds. The measured data points clearly trace a straight line, and the trend line equation confirms this linear growth pattern. The next slide begins our conclusion by comparing empirical versus theoretical results. In conclusion, for Part A, the theoretical time complexity is big O of n, and our empirical time complexity is also big O of n. Theoretically, linear search requires n by 2 comparisons on average, which gives big O of n complexity. This slide provides the final verification for part A. Our experiment validated this. As the array size increased from 10,000 to 50,000, the average execution time increased proportionally. The linear shape of the graph perfectly matches the theory. Therefore, the experimental result perfectly matches the theoretical time complexity of linear search. This concludes part A. So thank you for the attention. Assalamu alaikum.
Assalamu alaikum, sir. My name is MD Faizullah Talukdar, and I will continue the presentation right now. Thanks, Shoshita, for the detailed analysis of linear search. So, our next slide marks the beginning of part B, that is social network simulation. I will be presenting part B, the graph-based social network simulation. This project is centered on creating and analyzing a friendship graph using an undirected graph. So now let's go to our next slide. This slide refers to the specific objectives for part B. Our objectives for part B were to randomly generate friendships, which are bidirectional edges among users. We needed to compute vertex degrees and verify the handshaking theorem programmatically. Most importantly, we sought to determine the number of connected components in each network and analyze the effect of network size on connectivity. So moving to our next slide, this slide gives an introduction to our B1 social network model. This segment simulates a social network environment. In our model, users are represented as nodes or verticals, and the friendships are represented as undirected edges. By generating random friendships, we are able to study the essential behavior of the network, focusing on key analysis points like vertex degrees and connected components. So our next slide covers the underlying graph theory and model used. Our friendship network is stored using an n by n adjacency matrix. A user's vertex degree tells us their number of friends. We used the handshaking theorem to verify the data integrity. Connected components help us identify groups of users who can all reach each other. Our simulation tracked how this connectivity evolves as the network grows from 500 up to 2500 users. Now, this slide details the software and tools specific to the B1 simulation. The software and tools used for Part B were consistent with Part A, like CProgramming language for the simulation, VS Code for development, and Python for plotting the connectivity data. Moving to our next slide, we are now looking at the methodology used for B1 simulation in this slide. Our methodology for B1 involved generating the random graph, verifying the handshaking theorem with the computed degrees, and then using graph traversal algorithms to find the connected components. We stored these results and repeated this process for all network sizes before plotting the final graph. Our next slide presents the numerical experimental results for connected components. The results show a clear trend. When the network size was small at n equals to 500 users, we observed 39 connected components. However, as the network grew, the number of components dropped sharply. By the time we reached n equals to 2500 users, the network was nearly fully connected, resulting in only one connected component. Now this final slide for part B visualizes and analyzes the data. This graph vividly illustrates the results. The x-axis shows the number of users and the y-axis shows the connected components. The rapid drop from 39 to 1 components demonstrates a critical concept in network theory. As the number of nodes and random connections increases, the network quickly becomes highly connected, moving towards a single large component. So that's the end of my segment. Now I would like to invite my next teammate, MD Shahriar Hussain Siam, and present his speech to continue the presentation. Thanks a lot, sir, for the time. Assalamu alaikum.
Assalamu alaikum everyone. Myself Mohammad Shahriar Hussain Siam, and I would like to thank my teammates as Mohammad Fazullah Talukdar and Sumaya Saudagar Shoshita to describe the topics of CSE-106 project in a fascinated way. Now I will continue the project as components versus n. From the graph, we can see that it shows the relationship between the number of users denoted by n and the number of connected components in the social network. On the x-axis, we have the number of users, and on the y-axis, we have the number of connected components. From the graph, it is clearly visible that when the number of users is relatively small, such as 500, the network contains many disconnected components. However, as the value of n increases, the number of connected components decreases significantly. The trend line highlights this pattern, indicating that the network becomes more connected as the number of users grow. According to the next slide, the result can be interpreted as follows. With an increase in the number of users, the number of possible friendships also increases. Even though the friendships are generated randomly, more edges are created in the graph. These additional edges connect previously isolated groups, which causes small components to merge into larger ones. As a result, the overall structure of the network becomes more connected. This behavior closely reflects real-world social networks where individuals are often connected through mutual friends. To conclude, this project demonstrates how undirected graphs can be used to model social networks effectively. Our simulation shows that increasing the number of users leads to a rapid reduction in the number of connected components, eventually forming a highly connected network. The results also verify important graph properties, including the handshaking theorem. Overall, this project provides a clear understanding of how connectivity evolves in large-scale social networks. This brings us to the end of our presentation. We hope this project helped to demonstrate the behavior of social networks using graph theory and the empirical system of time complexity. Thank you for your kind attention. Hope you will understand our CSE-106 project. Thank you.